Our topic of today's Christmas webinar is basics in the lab, and because we are an electrophoresis company, of course the basics in the lab refer to the topic electrophoresis. So just as introduction, when you take a look back 30 years to the lab journals of your former colleagues, you will see a brightly nicely snowman, and when you perhaps look inside your own lab book today, you may find differences. So the snowman is not appearing as it was. So it may can cause trouble in your methods or your applications or not. You never know, but in last 2 years, let's say, we collected a lot of urban rumors, errors, tiny things that can cause troubles. So it was the idea to make a Christmas webinar with the most often issues we are fighting with in our technical support, and we made some points where you will find all these issues, and these are going with the workflow of a standard electrophoresis. That is beginning, of course, with a sample preparation, then with the casting of your gels. You use running buffers and running conditions where you can find issues. You stain the gels and you blot them, and afterwards you have a detection, and in every step in between you may find here and there some issues I want to talk about. So the general problems is, for example, that when you copy a method from a colleague, this is happening very often, I have to say. It is nice to have colleagues in your lab from all over the world, but they have, let's say, different kind of writing, and this is an example for it. For instance, in Germany, Austria, and France, the 1000 is written down with a point in between every third space. In England, UK, and America, they use a commata instead. Very special is Switzerland. They use a reverse commata there. And our recommendation is, of course, with the flag of science: do not use points, commatas, or else. Just write the numbers with a space in between. If you don't do this and you copy it, then it is very easy and very common that, for instance, 1000 microliters will become 1.0 microliter, and everything would go wrong then. So please be aware of this, and there will be no problems anymore. Then you do your sample preparation. This is the first thing you do, not depending on any application, but of course as well also in electrophoresis. The one thing is the mixture of different types of liquids, solids, and so on. The most often found is when you want to do a percentage of pure ethanol, you want to dilute it, you add water. If you use 50% ethanol, for example here 100 milliliters, and then you have to add the same amount, 100 milliliters of water, and what you can observe is that you have a loss of about, let's say 1 to 5 milliliters. So please just mix these two liquids and do not fill up, because if you fill up you will use more water or ethanol, and this will have not the same percentage you expected you wanted to have. Another thing is when copying applications methods, you often find such words like fill up or add. It's depending what you do if you decide to fill up or add. The worst thing is just to leave it away, because then you would not have a clue what to do. And if you already lost this information, here are some examples where you fill up. This is, for example, the pH value. If you have a solid, you fill it to the right amount with water, mix it, and you measure the pH, and the pH is correct, then you fill it up to the amount that you want to have. Adding is if you want to have a concentration inside. So you have your solid and you just add water to have a concentration and mix it, and afterwards you do not care about filling up to a special amount or else. Because this is such a strong issue in our technical service, we want to show it more in detail, how to prepare buffer solutions and adjust the pH. So first, please add your buffer and add your solvent, but not completely. Use approximately 85% of the total buffer volume. Afterwards, you mix the salts until they are completely solved. Then you go to your pH meter and you adjust the pH appropriate with the right acid or base. I will talk about this in a minute. And if you adjusted the pH, then you fill up to the final volume and mix again. So what kind of acids and base are appropriate for your buffer you want to prepare? Well, this strongly depends on the buffer you use. There are two examples here. One is the phosphate buffer and one is the sodium acetate buffer. If you have them, you should search for the acid or the base that is, let's say, already inside your buffer. For example, it's a phosphate buffer, then you would use the phosphate containing acid, or if you want to be in a base, then you use OH hydroxide containing buffers. What you do not want to have is that you change your ions inside. For example, do not use HCl, because then you add to your phosphate ions additionally chloride ions and you have a mixture of two different ion types. The same goes for the base. Try to use the same salts, for example sodium or potassium, and not something else for the same reason. The second example, you have the acetate here, so you would of course use the acetic acid, or the sodium, then the sodium hydroxide for adjustment of the pH. Next thing for sample preparation and solutions is very often made wrong. This is the reason that I show this slide again. It was from the Christmas webinar of last year, and this is the volume and weight percentage. So what does that mean? In the old Roman times, centum is the number 100, and this is referring as well in the percentage per 100. So for example, if you have 5% weight volume of sodium chloride, then you would use 5 grams of sodium chloride in 100, here's the 100 again, milliliters of water. For volume percentages, you use, instead of the grams, you use milliliters of ethanol, and you put them in 100 milliliters of water. If you want to get rid of some residues, then the best thing is to dialyze your sample. Many customers of us do not know exactly how to choose the right dialysis system. So there are two rules of thumbs where you can easily calculate yourself the range in between which the right mass weight cutoff can be chosen. So for instance, we have just a tiny example. You have a solution of albumin and you want to get rid of urea and desalting like. So urea has 60 Daltons. You can watch it or look it up on, let's say, Wikipedia or something else. And this Daltons you multiply by 5, and then you have the lower MVCO to choose. So it's 300 in this case. And this is the substance you want to have hold it back in your dialysis system. Albumin has 66 kilodaltons, and this is multiplied by a half. So you have 33 kilodaltons, and this is your upper threshold for choosing of the MVCO. So, for example, our express microdialyzers that can be ordered here at SERVA, you have 3 different sizes, and for this example, you could use all 3 of them. All would be enough and sufficient to go. When your sample is ready, you begin to cast your gels. There is a webinar explaining how to cast your gels the right way. Nonetheless, I want to talk about this special topic, and this is degassing of your monomers. This is very important because as the reaction of gel casting is a radical-induced polymerization, oxygen would inhibit this, and the polymerization would be very long-lasting. So an extent of the catalyst is required, and this catalyst is not really the cheapest thing, so you can spare a lot of money. And so it makes sense to remove any air, respectively oxygen, from your monomer solution. And how do you do it? You use such a bottle here where you apply a jet pump vacuum, and you put a closure on top, and you suck out the air and get a vacuum, and you will see that your monomer solution will begin to show bubbles. And when this is over, when there are no bubbles going out, then it is finished and you can cast your gels. After casting, you will load your sample on your gel. So there are 2 main problems by loading. One is that it is a rumor that you have to fill the well to the maximum. That is absolutely causing troubles. So if you don't want to have such an appearance of your sample, then it is good to load less. We recommend to load about maximum a half of the well. Everything above this will cause any distortion or streaks or what have you. The second thing is that you have to avoid concentration gradients in the empty lanes, or to have the same concentration on neighbor lanes. So what happens if you, this would be the right way to go, if you overfill the neighbor well, or if this well contains significantly more salts, then you will have this appearance. The salt overloaded, let's say, sample will try to expand to have more space for the separation, and the lane on the other side, for example this one, will have to move somewhere possible. So in worst case it will get very thin, and the two beside very thick. This is not very nice to see, so please avoid this and you will never have this kind of appearance here again. The running buffer, so after loading you have your system, your tris-glycine Lemley system, and there is a huge error that really a lot of people are doing. Well, on one hand because they are catch the right bottle, the wrong bottle, or yeah, just because they don't know this. So I just want to explain how the tris-glycine system is working so that you understand why not using tris HCl for the running buffer and how to avoid this. So first, on the left side, this is the state just shortly before applying the voltage. You have your casted gel here that has pH 6.8, and you loaded your samples. So you have your proteins here and you have glycine here, and this glycine at pH 6.8 has a plus and a minus load. So it seems that it is unloaded, but it isn't as well. But well, then in your gel you have your chloride ions and your sulfide ions. These are the ions from the SDS, so the polar end of the SDS. And when you apply the power, the proteins and the glycine will move into the first part of your gel. So and what will happen is that the glycine will stay in his, let's say, unpolar form. The chloride is very tiny, is very fast, and wants to move along really hard. And in between, you have your proteins that are loaded with the SDS, and they are minus loaded then, of course. So what is happening? The glycine is very slow and does not really want to go all the way, and the chloride is fast and wants to go through this very fast as well. So in between those two, there will be a narrow zone with a steep voltage gradient that is causing the proteins to stay in between these two molecules. And this is the effect you want to have, because afterwards, if you have your separation gel here and it crosses the pH to 8.8, then there is something happening. The chloride stays as it is, but the glycine is losing his plus and is fast, similar to the chloride, and will run through the gel very fast, and the proteins have time and razor sharp will be separated by their mass weight. So, and now is the critical point. In the good story, the running buffer is made with tris base. But if you think about something else, for example, your boyfriend, girlfriend done something, and you go to your chemicals and you just read, oh, it's tris, okay, tris, I take it, and you were not aware that you do not get the tris base, but the tris HCl. You prepare your running buffer, you put it inside. So what happens if you use tris HCl instead of tris base? When the glycine protein sulfide chloride will pass the gel to the separation gel, the glycine will stay in a more positive appearance, and then you have the same effect like in this narrow zone, not that much as it is here, but a little bit, and you will not get a good separation. The separation will be slow as well, and you have a zone electrophoresis then here. So to avoid this, please Be aware to use tris base and do not adjust the pH with ACL. Instead, you will have this appearance here and not nice gels. For running conditions, this is also something I already shown in the DNA webinar. Nonetheless, it works for SDS page electrophoresis as well. The current you apply to the gel is always dependent on the area of the gel you have. So the length times the height. And the voltage is your running distance. So many of you perhaps always do one gel, everything is fine, then your boss comes around the corner and says, oh well, perhaps you should do a second gel, for example for blotting or else, and you prepare one chamber with 2 gels and you forget to adjust anything, just let it run, and you, after half the time you think, oh wow, this is very slow. Why is it not running like always? Normally I have 30 minutes and now I need more than 1 hour. Well, this is the reason. For example, I think then you forgot that your area has doubled. So then you should double your current. Another problem is your boss comes around and says, well, all the time you made 8 centimeter long gels, perhaps we need more separation distance, please cast yourself 10 times 10 gels. You do this and the same effect occurs. Then you forgot to adjust your voltage, so if you have 8 before and 10 afterwards, then you should adjust your voltage by 8 divided by 10 to get to the same result. After the electrophoresis, you will in 90% stain your gel, I would say. There are many possibilities. The main ones I have here in this overview. The workhorse is for sure the Comasi blue staining. A lot of people use this, but also many use silver staining. Then another possibility is, for example, the lava purple or the SERVA purple complete staining. So this is a fluorescent staining. Or you go to a label, for example, our SERVA lightning red. The sensitivity is mainly known in the lab. So with Comasi you can detect, let's say, down to 20 nanograms. Silver staining, depending on the kit you use, you can go down to 200 picograms. What you can see, fluorescent staining and fluorescent labeling, of course, have the best sensitivity limit. But now we come to a point where you want to quantitatively measure what you have done. So Comasi is really a good way to go for quantitative analysis, but well, you have a low sensitivity limit. Fluorescent staining and labeling, of course, are the best way to go for quantitative analysis. Be aware that silver staining cannot be quantitatively used because it's no endpoint. So if you would leave your gel in your developer for too long, you will just have a black piece of gel where you do not see anything afterwards. But one word, and this is really done very often, so if you have fun on this, just go to your lab now, take your lab book and take a look on your Comasi blue staining. Normally, in 99% of all lab books, you find that after electrophoresis, you fix the gel, you stain it, you destain it, and let's say, depending on what you use, approximately after 3 hours, you do an imaging. I wrote it down here. Really? Because this is a short time. If you want to work quantitatively or if you want to have nice pictures, you should be aware that Comasi Blue has his endpoint in staining after overnight. in your staining solution, and then you should destain. So everything that is below overnight, you will see something, but it's not the yellow of the egg. So take a look on your lab book what you have inside. I'm sure you will not have overnight inside. The silver stain is of course a very long procedure, but if you like, you can try our SERVA lightning red, where you just label 30 minutes in advance of electrophoresis, you load your sample and you can image directly. So everything that is long-lasting or overnight, you just can avoid by using this very smart label there. Maybe you do not want to stain, you want to blot, you want to make an immunoplot. There are many possibilities to go. So you have nitrocellulose as membrane or PVDF. The binding capacity is a little bit different in between. The big disadvantage of nitrocellulose is that it is very fragile, so you really need to be very, very nice to your nitrocellulose if you want to have it in one piece. The disadvantage of the PVDF is that you have to activate it with methanol. Why do you have to do this? Well, the PVDF membrane is hydrophobic. So if you do nothing with it, and it happened to me once in the lab, so I'm not free of errors, I forgot it. I put on my sandwich, and after the time of plotting I found nothing, absolutely nothing on my PVDF, because the proteins are negatively loaded. They gets transported to the PVDF membrane, and there is nothing to hold on because it's hydrophobic, so it does not work. So the problem is that methanol is toxic. So many labs say, oh no, I don't want to go toxic anymore. So isn't it possible to use ethanol? So I have to be sorry. Can I activate, of course, PVDF? So this is a typing error of myself. Or substitute my methanol in my transfer buffer with ethanol? Yes, you can. That is why this Chuck Norris type here is putting up a thumbs into the air. Yes, you can, but you have really to buy a good quality of ethanol, because ethanol, especially cheap one, will have residues inside, other substances, or in the worst case, a percentage of 5 to 10 water inside, and this will destroy this activation. So use very good quality ethanol with at least 99.5% of ethanol inside. And if you want to detect your blot afterwards with horseradish peroxidase substrates, we have many calls and emails that are asking us, well, we bought a new imager from SERVA, but we are not sure what's happening there. When I used film before, then I just waited 1 second and I have really, really good bands that I see. And now with the imager, I have to wait minutes for it. I think the imager is broken. No, it isn't. And why? Here is the explanation for it. When you use film, your film is placed directly on the membrane. So the light of the horseradish peroxidase reaction is highly concentrated on your film. So if you develop this afterwards, then of course you have a high concentration of light on a spot. This is different with CCD cameras because the membrane is, let's say around 50 centimeters away from your lens and some centimeters away from the microchip. And this is also the reason why you have to wait longer. Well, the light is diluted, let's say, in all these 15 centimeters, and some of the light is then then put together on the chip, but you see it in this graph not as much as the film directly on the membrane is. And this is the reason why here you have seconds to go, here you have minutes to go. Another thing, let's talk about the bad chemicals in the lab. This is also something that we have to struggle here a lot. Ethidium bromide for DNA gels is really not wanted anymore in the labs. So many companies sell substitutes for ethidium bromide that are not cancerogenic anymore. What they do not tell is that you maybe cannot detect it with the same light source. So people think, well, I used ethidium bromide with an UV table and I just take the substitute and get the same results. That is wrong. And why it is wrong, I show you here. So the red line here, the really red line, is the spectra of ethidium bromide. And what you see is that this spectra has a maximum around the 300, so it's UV light excitation, and but it has a second one, a smaller one at let's say 500, around that. And this is similar to the red substitutes you can buy. So for example, gel red. This is nearly the same. So it really strongly depends. If you use UV light, you get a high signal, a very strong signal. So you will see a lot and your background signal ratio is very good. But ethidium bromide can also be excited by blue light, but with an intensity of, let's say, 1/8 or something like that. The green substitutes you can buy on the market, this would be, for example, our DNA stain Clear G, it's vice versa. So they have a tiny small excitation maximum in UV light and a high one in blue light. So it is still possible to see the green substitute with UV light, but of course 1/8 less than with blue light. So please, if you change from ethidium bromide to any substitute, take out this sheet and watch what you need, if you need a UV light or if you need a blue light, and then you will really be happy with your results then. This was it from my side. I hope you liked it and I'm open for questions if there are any.